So welcome then to lecture number 10 in network security. So last time we have started with malware. I looked at some specifics for the SQL slammer, but today we go in more detail about viruses, worms, trojans, maybe also this malicious document malware, and to see what are the common let's say approaches, what can they do, and what is the common counter measures that we can do. So first some definitions. With a virus, so probably, and at the end of the lecture, hopefully you can also say what is the malware in the document, in the Windows Word document type. So what is a virus? Is it a virus? So a virus replicates itself. It spreads beyond the boundaries of a single system. So typically this is the core element, that it replicates itself. So it has several activities. So if you start it, then it has a self-replication option, not option, but it's mandatory. So it looks for other files that it can copy itself into, so that next time the other files are executed, they also self-replicate. Then it typically has some kind of other activity, but doesn't have to be. So it can do some damage, but it can also do nothing else. And then you have the regular activity, so that it doesn't look suspicious. So typically you just, I don't know, back in the days, when let's say 20 years, or let's say 30 years ago, when people, so I had also my first PC, and just totally uncorrelated to that, how did the people exchange software? They just exchange floppies and so on, not related to me. And sometimes if there was a virus on one PC and it executed, and it also attacked, basically copied itself into the programs or in games and whatever they had at that time. And once the data, the floppy was handed over, or the CD-ROM or so, then it was also executed at the new machines. But it can also be a USB stick that you find somewhere and that you attach to. And there's some auto execute for some kind of program on it to display some icon. I don't know how to auto start some kind of installation process, and in the background the virus is executed. So any kind of external media that you get and don't trust might contain some executable with a virus, but you always have to actively execute it somehow, or you download some very fancy program from the internet, from suspicious sites, that promises you that you can use, I don't know what is fancy nowadays, ChatGPT locally with 2 gigabytes of RAM, and you can create your own AI, whatever, and it might contain some virus or any kind of potentially suspicious sources might have an intention to that you download some kind of software, execute it locally, initiate the self-replication. Typically the other activity nowadays is that it somehow encrypts all your files and asks for a ransom, so that you pay money to get them unencrypted. But the core element is the self-replication. So why are they interesting? They don't cost any resources to the attackers. They just have to create them and then spread them somehow. Yeah?
A question. So this also implies that whenever a virus is executed, the actual disk usage increases of the operating system?
It should be. The file sizes that they modify change, yes. And this is one way also to detect that something happened, because typically file sizes should not change, especially in executables, and this can be basically looked at and analyzed by counter measurement software in order to detect some infection. Yes. Okay, so it's very easy, and sometimes it's also, I think it has also been partially done. So now partially somehow, I think that there will be some malware. The Stuxnet that has been deployed in Iran at one time to attack their centrifugal machines. The code for that was also somehow deployed by some random USB that was executed within the facility. So always be careful if you plug in some unprotected devices to your system. So what can it do? And what are so if you are a malicious attacker, what can you do? The question is, so first of all, you want to build this virus and then somehow have a second use of it. So what could be the second use of it? What could you do? What vulnerability could you use to exploit to run the virus without actively executing it? So there are, again, some kind of nice features of Windows that is more for comfort, but that pose some kind of security threats. So for example, if you plug in some CD or I don't know what USB stick, and it has some auto installation, it has a pop-up, it has some kind of loadings of some specific icon for displaying that specific drive, that can be also all used. Spreading beyond boundaries, that's a little bit tricky because it overlaps with the worms that we will later focus on. The question is, how can you program a virus? How can you detect them, and how can you prevent being detected? So previously, viruses were quite more difficult to program. You had to type yourself in assembler. You had to think of the placement of the virus in the code. Where do you want to place it? And you have to keep in mind, so if you have a virus file and it first needs to detect a regular executable, so it needs then to copy a part of the virus over in order to have the same virus functionality basically. And you have to modify the file in a bit that sometimes in the execution, so typically the instructions are executed one after another, but you want to have the virus part executed as well. So you have to think of, where do I place it in the file? How do I change the program counter at some time in the execution of the file so that my virus code is executed? So you have to think about the file setup. Nowadays, it's getting easier and easier to compile complex systems. So you can now, there are some virus construction kits with specific libraries that click and point and so on, so that you can easily create them. It's one of the benefits, from the attacker point of view, why are they doing this? They try to, because if you have an executable and it does some harm at the local machine, you are so far remote from it, so the attacker is not really attached to it. So this happens somewhere at home, somewhere in business, in companies. So what's their gain? Their gain is twofold. Typically, obviously they want to make some money. And one option is that you have this kind of ransomware where you encrypt all of the content of the hardware, of the hard disk, and then you ask for money to give back the data, to decrypt the data and make it available again. So typically state, official institutes, cities and so on are victims of this. And the other option that you want to do is that it becomes a bot in a botnet, so that you can send some kind of commands to it so that it executes some activity. So one of the attack options that you have for botnets is, if there's a website that you want to attack, somebody's paying you to attack them, you send out the commands to your bots and they are attacking that website, so that if the website somehow traces back where did the attacks come from, these are all innocent victims that didn't know that they are part of the botnet. Okay, so nowadays it's easier. We won't go into more detail. We will more have a look in the elements of how antivirus software detects this element. So let's say we have a virus or some malicious activity in an executable file. Maybe also we can also extend it to Office documents. So what would you look for? How would you approach it? So how did you do it? So if you wouldn't have the LLM to look into the file and to analyze it, what would you have looked for?
In the Office documents.
Yes, in the Office documents.
File structure for static and all the VBA helps also to get some stuff. So usually what's written, what can I read, and then what does this imply?
Yes, so basically then you would look for some kind of things, some kind of patterns, some kind of strings, some kind of configurations that you know of that it is strange or malicious or so. So let's say in your case you have this specific VBA file name that is loaded from somewhere and executed. Then you would know, okay, now I know that there's this kind of attack, and everywhere in every Office document I find a specific strange file name, I would consider it as malicious. Yeah, because the probability that you had this, I think, 1620 character long string combination .exe or so, if this specific combination pops up, then it is considered malicious. So basically what they do, they scan files specifically, so they look into, actually they also open every executable file, they look into it, they go through it, and then they look. So where is it written? Then they look for patterns actually. So there's a corresponding pattern file that lists all of the malicious, the known malicious patterns, such as the file name to the attacking file, and then they would flag this specific file as potentially malicious. So they scan existing files, they scan new files, they scan also. So this is one approach. So basically you look for patterns for specific strings. So these patterns are strings in the file or bit combinations that look suspicious. And the other approach is that you look for calls and interrupts before they are forwarded. This is more the dynamic or the active mode, where you have a specific kind of sandbox and that would like to interact with the hardware, so to call interrupts and system calls and so on. But there's some kind of virus scan interface that basically is acting as a wrapper interface, and if the access pattern becomes abnormal, then it would react. So also here you have the static approach and the dynamic approach. Dynamic means that the file is executed and you observe its behavior, and the static approach is that you look at the file as it is and try to identify malicious patterns. So now there's a cat and mouse game. So let's say there's a virus and some properties are developed. It's very similar. Okay, so let's say it's written. Okay, so this is the file. This is the replication part. Yeah, replicate. How does it look like? It has information like open other files. It has some part like copy parts over. And if you have, I don't know, 5, 10 instructions one after another that goes into this direction, this can be flagged as a pattern that should not happen regularly. And every time, every executable that you identify with, and you go through the instructions and you see this kind of pattern, then you would say this is a potentially malicious file. Okay, so this is how the producers of antivirus software basically extend step by step their signature file. The signature file is the list of this kind of patterns that happen, that are known, and that are used for detection of potentially malicious viruses. So, but the attackers also have access to the signature file and to this antivirus software, so they can download that antivirus software themselves, and now they can make some modifications here and there so that the pattern doesn't apply anymore. So it cannot be longer detected. What's the consequence? The antivirus producers now have to catch up on the new pattern and try to extend their signature list with this new pattern as well. Here we have a very simple doc file, COM file, an executable. I think it's also part of the exercise now, where you have to modify and to write a virus. So basically, there's some kind of mandatory prefix that is somehow describing this is a COM file. This is the file plus 100 bytes, and what it tells is jump with the executable. So this is the first instruction it should execute. And the first instruction tells to jump at byte number 400, and here the instructions are all written out and you can follow up. And if there's some kind of data that it refers to, I don't know, loading some variables, it can load it from the space between, that's probably 132 or 100, it depends on how much this is. Let's say 132 if it's 104, so it's 32 bits maybe, so 4 bytes more, and the data starts at byte 104 and the code starts at byte 400. So this is a very simple COM file that has here the instructions in bytecode, that is machine code that is accepted by the CPU. Okay, and if now a virus comes along and wants to modify this file to copy its self-replicating element inside, what it could, for example, do, what would you do if you don't have a look at the slides? So what would you recommend? Where would you put the self-replicating code? And how would you include your malicious part of the code? So somewhere you have this part of malicious code that you need to copy into the file and make it executed.
Maybe in the data?
The data would be an option, but let's say here you have crucial variables like, I don't know, a equals 10, b equals 20, and it's very crucial that you keep this kind of configuration. You cannot override it.
How big was the data copy?
It's 300 bytes. Maybe we need 500 bytes for our virus part. It's just important that it is somewhere in the line of the execution. So if the program is started, so probably there's program segment prefix, probably that there's some kind of I would assume that there's some kind of jump to 100. So if this is the first command that is executed, it jumps to 100, then it jumps to 400, and then it executes these kind of instructions that are here. I don't know, a plus b, print result, don't know. And you have this new kind of virus code that you have to integrate somewhere. Especially, so this is, then it jumps here too, then it jumps here too. So these are the instructions that are executed. So you somehow have to put in your virus code to be executed as well. That would be an option. Okay, let's put it here. Then we do not obstruct anything else. So everything else remains as it is. Yeah, but here at the end you have some kind of loop and you jump back to 400. So it's never executing the last part. You don't know what the code does, whether, I mean, it should not terminate. Sometimes you have code that's not terminating, that's always waiting for your input. Yeah, but that's already a good point. So what you could do is to say, okay, we don't jump to 400, but we jump to 800, execute first the virus, and at the end we jump to 400. And by this, you make sure that your code is executed first, and then the rest, the regular code, is executed and can perform as it has been planned. So it's very simple to modify. You just need to make sure that in the execution line of the instructions. So, where have you heard Rechenarchitektur? Rea, with whom have you heard that? with me, with Professor Lang?
No. So it's been a while.
Okay.
Das ist noch lange her.
Okay. So I mean that's a very simple thing. Is an executable file is typically, let's say, if let's make it easy, with 32 bits. Nowadays we have more 64, but here you have some kind of bit patterns that are specific for the instruction set of the CPU. So typically you have here some kind of operator like plus, and then you have here operand 1, operand 2, and maybe some kind of how's it called, some kind of constant, I don't know. So this might be a plus b plus 5 or so. So, and all of these possible bit combinations that you have there, whether that's an operand and operators, so basically defining the function that you apply to it and what is the input. So this is all specified, and this is how the EXE file is set up. So it's basically a list of all instructions for the CPU that it's executed. So what you just, and how does it perform? So first, the program counter in the execution reads the first line. If it's done, the program counter is increased by 32 bits, so by 4 bytes. It reads the next line, then the next line, then the next line, and so on. So the only thing you have to do is to make sure that somewhere in this your virus code is executed as well. And the simple way is to jump first to the virus code, then this is executed, and the last command is to execute this part from byte 400 on. Okay, so how can the antivirus software detect and remove this virus? Do you see a pattern that could be a hint for detecting the virus?
Yeah, I mean, it tries to access code outside of its.
Yeah, but I mean, now the file is ending there, so.
Inflated, so it's longer.
Sorry?
It's longer than now the program.
That's right. Okay, we can. So what we can do is basically keep track of the size of every executable at the machine, and once they change the size of the executable, that's a little bit strange, and we could have this as a sign for potential maliciousness. I must admit that some files still change their sizes. They extend this part big and small. I also had some programs previously that somehow, it was some games that stored a save file in the file itself. It was very strange. But okay, what you could also do is to just know, okay, for example, but it's a question whether in COM files it's always the same. So if you would, for example, know that COM files should always start at this point, this is the fixed setup, I don't know, 300 bytes for data, and then it should always start at 400, then you could check whether there's some kind of jump at the begin which does not go to 400. That could be also some sign. It really depends on the file type that you could look for. But let's assume we would have as a countermeasure the pattern that in the begin there should be also always jump to 400. What would an antivirus, what would the virus creator now do? What could you do as a, so let's say you have to live with this constraint. What constraint? One moment. Let's delete this. So let's say this is not allowed anymore for you for creating your file, your virus, and you have to stick to jump 400. How can you reach your virus code now? Any idea what you could do?
We put the virus code at 400 and move the code below.
Oh, that's also possible. Yeah, that's right. You could also exchange this part. So basically, you slip it in there. I'm not okay. That might be an option. I'm not really sure. Sometimes the code here itself has a relative reference, so it can say a plus this address minus, I don't know, 500. and it's referring to a specific position in the data. So it might also be that shifting that code is not possible, but you could try. What you could also do is, I mean, the code is typically not straightforward. Sometimes you have if then, you have some kind of jumps yourself. So if you have some kind of recursive function, then you have anyway some jumps. If you have some kind of method call, then you have also jump, because the method is typically, let's say, defined back here, and then you have to jump there and then jump back. So basically what you could also do is to analyze, if I would execute the code normally, what is the first jump or the second or the third jump that happens? That probably isn't such a big deal, but I could change it to jump to the code, and once the code is finished for the virus, I jump back. So you can basically replace any kind of regular jump in the virus, in the regular code, with a jump to your virus, and after that the execution continues normally. So that's why sometimes with dynamic detection it's questionable. So it's difficult to know, did we find the code or not? Did we find the virus or not? So let's say you would hide your virus in the code, but it only is executed at specific times, let's say at 6 p.m. or so. Then, and if you start the dynamic analysis at 2 p.m., then for the first 6 hours nothing happens. So everything is regular, and you will not test it for 6 hours. So the question is, that's a difficult part of dynamic testing, that you really have to, that the virus has to be active at that time, and the right conditions must meet. So the benefit of the static analyzer is that you could detect these kind of patterns. But okay, let's say we would also be able to detect this kind of jump. Okay, so here first summary. So we use signatures to detect known viruses. A signature describes a detectable characteristic of a virus. If you think back at the intrusion detection systems that we had, it's very similar to it. So it's an intrusion detection system is actually a virus scanner for networks. Let me just see, where did we have it? Do we have here the snort rules? Exactly. So this was the network intrusion detection system, which basically looked into the traffic, the payload of a regular file, of regular packets, and if, for example, this pattern came about, user agent 3a asafarweb.com, then this was considered as a malicious activity, and there's an alert, I don't know, malware CNC user agent. Or if this happened, this is a signature, this is a pattern. If this is identified, this is a pattern. If this is the file name, this is a pattern. And very similar also with regular file, with regular antivirus software. If you identify a pattern in terms of a set of instructions one after another, or access to specific address fields, this is how you say, okay, now I have something malicious at the hand. So simplest form is a distinctive sequence of bytes. Often it's more also with wildcards and allow mismatches and so, but basically you have a pattern matching. Okay, and also you can focus on important parts of the files in the beginning, at the very end, where viruses are often placed, but you can also go through the whole file, and you are looking just for this bit patterns, for this instruction patterns. Okay, let's say you are an author of viruses. How could you counteract this? So if you know that, let's say there's a specific, what was our example here? Let's say they are looking for this pattern, asafarweb. Okay, so every time asafarweb, so this is just an analogon of, obviously, but also in viruses, if there's a known pattern that you have to avoid, how could you avoid displaying this information? How do you provide confidentiality so that not everybody can read what you want to do? you have some data that you want to hide from interested eyes, and they should not see it. Only once it's executed, it should be visible, let's say. How could you do that? Yes, we can encrypt it. So what we can do is we encrypt this, and this, I don't know what it gets, yeah? And in the code, this would be written, and once it's executed, then you decrypt it, and what you get is, again, what you put inside. So you could use an encryption method. Let me just see, one moment. Yeah, so, okay. So, if viruses contain constant sequence of bytes, then they can be easily identified by using signatures. So what we do, we can use encrypted viruses. We add a decryptor and the main part. So basically we encrypt the virus and we give a decryptor that is able to decrypt it once executed. So as long as the infected file is not executed, we only the signature is not visible. Why is it missing? So then you cannot detect it basically. And then once it's executed, the decryptor decrypts the main part and executes it. Okay. So also, if you have this replication element, yeah, if it's included in a new file, you can encrypt it with a new key. So basically you can store in the file, what do you need to store in the file then? You have the encrypted element with some key. Here's the virus. You could also add the key because it's just a random set of bits that is used. And what do you else need? Decryptor. So that the decryptor can use the key and decrypt the virus. Simple example of encryption code, you take an XOR with this key and the decryptor simply loops over the code and XORs it with the key. You can also, yeah, I mean you don't have to make it too complicated. So how do you detect now the virus? Or how do you detect now that there's something malicious ongoing? If this is now what is stored in the file, I mean obviously there's the regular code. Basically, the virus acts, if once it's called, it calls the decryptor to take the key and to decrypt the virus. So, how do we detect now the virus and its maliciousness? What would an LLM look for?
The encrypted part should always be the same, right?
No, you can change the key from file to file. It's just a random set of bits, 32 bits let's say, and that's always XORed with the virus blocks. And for the next, once you copy it to another machine, you take a different set of of keys, different set of 32 bits, and you XOR the virus and then encrypt it with that new key. So every file has a different. So what is different in every file? This is different in every file. This is different in every file. What can you look for? So if this is all different, so because the encrypted virus is all different in every file, there are no patterns. If the key is different in every file, there's no pattern. What can you look for? Yeah, the decryptor, yes. You can look for the decryptor to identify is there some kind of decryption ongoing and happening in the code. That could be your new lead for identifying the to identify that there's some kind of encrypted virus. So searching for the decryptor is the next way, and this is static, and you can also do it dynamic by basically running some kind of debugger, running some kind of sandbox environment, and once you see that some kind of decryption happened, then you stop the execution, and then you run the signature checks on the decrypted part. Then again, how long do you wait until the decryptor gets active? What if the decryptor gets active only at 6 o'clock, and you have to wait 7 hours or so? Will you ever manage to execute it or not? Do you wait long enough with the code in the sandbox to observe this or not? Okay, let's say the defender can now also identify the decryptor, and once the code is decrypted, it can look for the known patterns. What could we do?
Decrypt the decryptor.
Yeah, we could. That's right. We could create a chains of decryptions, and at one time, hopefully, that the sandbox environment gives up because it doesn't have so much interest or in execution time to invest to analyze it. That's one option. But you could also go back to the signature detection. So let's say if there's a set of known signatures, so the execution code is somehow known to be malicious. Because let's say there's some kind of A equals 10, B equals 5, so C equals A plus B, print C. So let's assume this is something malicious. I don't know. In your case, let's pick up your case. Let's see what the file name was. And let's see, is this the final one? Yeah, let's go to the, where's the file name? Yeah, that is, it's quite funny story. One moment. So let's take a specific, this specific file. I don't know. So this is, let's say, our signature that we want to hide. How could you load this file, create this file name without having this file name in the code? So that's a nice thing about, let's say, combining. So let's say you want to open a file name. Yeah, this is the file name that you want to open, but you don't want to have the file name listed in the code. Is there some way to do so? So what would you do?
So I think it's called obfuscation techniques, where you define a string before that. For example, NPLD. So
Yeah.
NPLD, and then you refer to the downloaded file. You do, for example, string replace or something, or you just concatenate it.
That's right. So what you can do is something like open file, I don't know, P as R plus A plus, I don't know, 7 minus 13 plus 6 plus, also small letter B. Yeah, so that you step by step basically have a very long similar explanation what you want to do, but the file name is not anymore visible. This is obfuscation, yes. So it's basically let's jump. Okay. Yeah, this is basically the polymorphic viruses. We will also look at the other elements. But polymorphic viruses is if you have some specific settings. So here, for example, this is an XOR of two longs. So basically what is done here is A equals 0. And A equals 0 would be A equals A XOR A. Yeah, this is equal. And you can also say A equals B minus B, and you get the same results. Basically, you exchange parts of the code that are part of the signature to make it look different. Insert meaningless operations that does not disrupt. splitting the decryptor in several parts which are connected by jumps, so then are not 5 instructions one after another, but one instruction, then a jump, one instruction, then a jump, and so on. Maybe let's stick to this. How would you detect now this kind of activity? How can you reduce it to something that you can detect? Because obviously the set of potential alternative implementations for the same semantics, for the same code, is uncontrollable. So you can have millions of synonymous replacement for a equals 0. So how could you detect that? It's not anymore possible in a static manner, I must admit, but what you could do is to try to optimize the code. So if you optimize the code, then this would be replaced, this would be replaced. So all elements that can be pre-computed, because they always result in the same, that could be pre-computed once, and then you get synonymously always here this equals to 0. And also this, if you pre-compute it in what changes at all, what is possible to change, then you would also see that A is after the declaration not anymore modified, so you can simply create it and add it in. This computation always results in the same results. Small letter of B is always resulting in the same. So if you basically optimize the code, pre-compute what can be pre-computed, and put it then together, then you see some kind of, then you remove potential distractions. So this is the element of polymorphic viruses. A little bit simpler way, this is here the idea is basically during the round time, so during every generation you would, as a virus creator, modify the code somehow. But of course a simpler option would be to just have oligomorphic viruses which have just several or many decryptors, and they select one by random for the next code, and the rest is maybe encrypted as well. So it can be transferred to the new file as well, but only one of the decryptors is at use. Okay, let's let me just see. Okay, what can the viruses do themselves? Is we have so let's say it's already quite difficult for this to counteract. Yes, you could optimize the code, but it's getting more and more difficult. What also the viruses can do is to have metamorphic viruses, so they change. So what they do, they bring their own source code, they disassemble themselves, they scramble the code for changing the function. So for example, A equals 5, B equals 7, C equals A plus B. That could be now B plus equals 7, A equals I don't know. Yeah, so it could of course introduce unnecessary computations as well. And C equals B, and C plus equals A, something like this. So it's mixing it up, and the order of the executions is mixed up, and the parts of the executions are new. And then it reassembles itself to generate the next generation. And you can also adapt to different operating systems, to new environments, to new processors as well, if you bring your own compiler with you. Any idea how you can detect those? So one question is, do they bring their own compilers with them? That could be something to identify. If they're using the system's compilers, then it's getting more and more difficult. So at one point, with all these executions, static analysis will come at the end, because you can try to follow up all of these patterns on how the code can reshape, but it's getting more and more difficult to have one distinct signature, one distinct pattern, how the virus looks like, to identify it. So it's at the end, on all machines, the virus looks different, so you don't have any commonalities. And then you will need dynamic analysis. So jumping to dynamic analysis. Yes, so this is what we also had, for example, starting here. You put the code, the virus code, so you don't know whether it's a virus or not, but you put it into some kind of sandbox, and all API calls to the hardware are monitored. So by this you have the ability to identify, is there some execution, maybe is this executable, I don't know, maybe it's a screensaver and it opens 10,000 of executable files. Looks suspicious. So you could monitor the system calls, the file openings and so on, API to hardware. And based on its behavior, you can make a decision. So what could the virus now do to not be detected? It can. So it can use itself. It's a quite funny thing. So what it can do is it can try to set up its own debugger. To not execute directly with the hardware when the execution is happening, but to use some kind of local debugger and to use the interrupt 1 and 3. These are used to realize step-by-step execution and to have a breakpoint, so you operate until you reach that. So, any idea how using this integer interrupts 1 and 3 might have an effect? The effect is that the execution down here is also using interrupt 1 and 3. So basically, we have a debugger running on a debugger, and the question is now which one, what is the outcome? So if we are using up here the debugger interrupts, and then we notice that we cannot use it properly, then we know somebody else is using it properly. And if we know somebody else is using it properly, then we know, oh, somebody's watching us. If we cannot use debugging anymore, then we know, okay, we have to behave politely to not be detected. And then we have simple case. So if we can use the debugger, then we operate maliciously. And if we cannot use the debugger, then we are friendly code and we don't do any malicious activities. So and then that's a nice thing. So the question is, how often do you apply the sandboxing to the executable file? Is it reasonable to have all software all the time running in a sandbox? That's causing some overhead, causing some delay, maybe some resource consumption. So typically what is happening is that for the first few times you have a look at it for some specific time, and after that it's assessed as potentially good, yeah, without any harm. And the next time the virus is executed, then it can cause its malicious activities because it's not anymore debugged. Okay, yeah, that's basically. So I will not go too much into detail. What it does is, how can it detect it? It tries to detect whether it's executed in debugger. It puts trace information on the stack. So basically, to have a look. So this is some kind of information that should remain if no debugger is in use, and if a debugger is in use, it should be modified. So this is some debugging backup information or some kind of processing information. So it puts it at the stack, and it's taken off the stack before executing an instruction, and puts it back at the stack afterwards. So it's always somehow keeping the stack, so the debugging information on the stack. And if there's some modification of the stack, somebody changed the debugging information, it was not us, then obviously somebody else is using the debugging function. So we put basically some kind of stack pointer, extended stack pointer to a known value. We store it on the stack, we load it from the stack, and then we compare, has it changed? If not, then we behave maliciously, and if yes, then somebody else is looking at us and you should do something harmless or confusing. So, okay, what else can we do? How else do we progress with dynamic analysis? So basically, we just run the code that we want to operate. This is the sandbox mode. As I said, it's accessing the API offered by the virus scanner. It does not access directly the hardware. And what we do is just to observe it for some time. So we emulate it, we just run it, but in this controlled environment. And every time we see something misbehaving, then we assign some kind of maliciousness score to it that can be at one point exceeding the regular range. Yeah, this is some example how code emulation happens. So basically, while the sandboxing is in place, we get the opcode. So this is the instruction. So the instruction contains of the opcode, which operation is executed, operand 1, operand 2, operand 3 maybe. So this is, for example, op1 equals op2 plus op3. For example, I mean, they could be registers. And if it's a plus operation, so if it's a sum, I don't know, then it's described here what should happen. So basically it is a recreation of the functionality that the CPU should do in software so that we can observe what it's doing. What are the pros and cons? Why is it not applicable too long? Yeah, this is quite slow. So this is recreating something that runs on hardware on the CPU and it's very fast, and recreating it in software is too slow to really be operational reasonably. So it's okay for some time to observe what's happening, but it should not should not run in this environment for regular time. Okay. Challenges, especially for this encrypted and polymorphic viruses that change during the execution and during the copying. We can only look at the patterns in plain text. So we look at so the encrypted viruses. If there's a virus and it's used at encrypted, at one point it will decrypt the code, the virus code, and then we can observe the virus, the code memory, and see there's the patterns that we are looking for. Challenges: where do you start looking? How long do you wait until something shows up? Yeah, this could be part of the virus signature. So if there's, for example, some decryptor that quite quickly decrypts the virus, then you can say for this it's sufficient to wait 5 minutes. And if something is known to wait for 1 hour, then you wait for 2 hours or so. So you could put it into the virus signature as well, how long you wait. Yeah. But it's, I mean, you're always behind somehow. Let's say 98% of the known viruses are covered, but 2% are not, and they are always new generated. So what you could do is to characterize some regular behavior that you do not anymore look at signatures. This goes more into the direction of anomaly detection. And you know how files typically behave, and if something opens 10,000 files, executable files, and modifies their sizes, this might be suspicious, although there might be also some regular applications for it, such as hard disk compression. What else do? You optimize the virus code to be searched for. So you, before running it, you run this pre-computation. What can be pre-computed should be replaced. There could be some suspicious locations in the beginning, at the end, at the first jump, and and then hope for the best that you find something. But virus creators can always outsmart you. They can set up some kind of new, I mean, every new virus doesn't show some kind of known patterns. It will not be detected the first time, only if it's had some spread, then it can be identified as a pattern. Also, if you use old files, old viruses, the question is, if you have, for example, this kind of admin bomb, where an admin, isn't it, where did it happen? I'm not sure. Did somebody set up something similar? So basically, there are several stories where admins placed specific crucial, they put on their website a file with a bit 0 or 1, and if 1 is set, then the code executes in the industry environment at their employer regularly. So the code, before executing it, looks up, is there 1 on the private website of the admin? And if yes, then it's executing normally, and if the admin is kicked out, then it puts a 0, and then the code doesn't execute anymore, and you have this potentially malicious activity. You cannot emulate and look into the code for so long to detect all of the options. We had this metamorphic, yes. So it's a little bit mixed up. So what is typical anomaly or normal behavior? That's the main question. So what should we look for if it's about anomaly detection? So what is strange? Yeah. If it searches for executables in certain directories, if it executes or if it modifies its own code, if it jumps first to the end of the file, that's also suspicious. And there might be also other suspicious activities. If there are, for example, quite early a set of XOR computations that are suitable for the decryptor, and the length of the decrypted data is not larger than the file size, that looks strange. Yeah, problem, there's no guarantee. Also, harmless programs can be classified as viruses, hence the term of heuristics. Yeah. Okay. From the timing, yeah, let me just have a quick look. And you can also think in the meanwhile, how should code be tested for malicious activities? Okay, let's. So how should how should code be tested for potential maliciousness? That could be also some question that you should look into. Okay, we will pick up that the next time. We'll also have a look at the potential new targets, and then we will complete the malware observation, and still have done a few bit time for TLS and so as security protocols. Okay, thanks for today. We will see each other in the next exercise.